Like the last 5
Yeah.
minutes.
So cool.
I was so tired.
Oh, yeah.
Or like the family guys, whatever. You feel really sleeping.
Get this out there.
Where's James?
Huh?
Oh my god, it's cough.
What?
Oh, yeah.
What'd you say? I didn't hear.
Jack's
Saying like.
I think I'll get back here.
Or like.
I wasn't even figuring it out.
Pretty much.
Yeah.
My god. Thank you.
Oh, sir.
Oh my god.
Oh, my God.
Sure, Giddy.
What
What are your grades?
So.
So. What's your GPA? Over under 2,000.
What?
You guys. It's like.
I have not seen
This.
You're in like.
No, it is.
Okay, folks, let's see where we are. Okay, have I shown you the calendar like this before?
People try.
Thank you. This is where we are now. I forgot to write it down, so it's like together. We are April 7th, right here, Emily, so we're the red ones. Let's just see where the test is. Dun, dun, dun. Dun, dun, dun. There we go. Yeah, so April 22nd is when the test will be.
With this.
I'm only missing the review.
Now, it is a pretty short quiz. I'm not, a pretty short section, excuse me, pretty short unit. I'm thinking about having a quiz on,
Is that this Friday? No school?
Oh.
No.
oh. Next week it will be this Friday. Wait, what?
Next week.
Next week it'll be
Friday.
Friday, yeah. All right, so when we're here, this Friday there'll be no. But
So
so
next.
Next Friday we go to school.
this Friday, we'll be celebrating Shabbat together, just so you know, yeah. In an algebra 2. What's that? Okay, so this is a little bit of a mini unit, and actually the assessment that we're having is not a full test. I think it's gonna be like a 50-point test. So it's like a half test, because it's not a whole lot of information here, but it is essential. Oh, so yeah, so what's the date that the test is on?
Day 6.
Did you get the 22nd? That's like a Tuesday, right? It's 22nd. And quiz, I'm thinking a quiz day 4. And this will not be the normal kind of like review the whole day and then take the quizzes. It's good. I'm gonna stick in a quiz and make it happen.
Where's he mean?
You'll be taking it next to your partner, but that's it.
What do you mean?
Like normally, we take a full day for the quiz, where I give you a review sheet, and then at the end of the class, we take the quiz. So this time, you just need to be prepared from the previous 3 days to take the quiz. There's no review for it.
I'm just gonna take a quiz and leave.
Well, we'll have a class and take the quiz. Because it's going to be on day 4. So we're going to be putting it all together, fully graphing rational functions. Quite possibly. So if we have a quiz, that's when it will be. Just give me a heads up.
What if we took D4 really slow and the lesson took like a whole hour?
So then we just have 15 minutes for the quiz.
Take the best.
I don't know, we'll see. We'll see. Oh. Anything could happen. But let's get to it. Okay, so in previous units, we were talking about end behavior, and would you please discuss how you are supposed to talk about end behavior mathematically? The first word is as. Go ahead and discuss with your partner. What's kind of sentence are you supposed to put together?
Is there any what?
Not today.
What?
Can I call? Can I call someone? You ready? Oh. No, it's not you. It is Gideon though. Gideon, what are we looking for here?
X goes blank, Y goes blank, and then.
As X goes to something, Y goes to,
So it's Y.
nice, okay. So could you give me an example of just like X goes to like how? Okay, and could you all give me a visualization of what this looks like with your hand? As what X goes to infinity, Y. And of course, we could also say as X goes to negative infinity. And if this is Y goes to infinity, then this would look like this, right? It's going up this way. Today, we're going to mix it up just a little bit, and we're going to talk about as X goes to, we'll say things like as X goes to 3. Now, X going to infinity kind of makes sense, doesn't it? The numbers are just getting bigger and bigger and bigger. If X is going to infinity, like passes a million, then goes to a billion, then goes to a trillion, it's getting bigger and bigger. But what would it mean for X to approach a number like 3? Go ahead and discuss with your neighbor. What does that mean?
Oh, yeah. No. So positive stuff. Yes.
Okay, yeah, so what does it mean? Like, does that just mean X equals 3? And what does it mean X goes up to 3? Does it go up to 3? Hey, gentlemen. So X stops at 3? Are we good with that? X stops at 3?
Yes.
Kind of like a minimum and maximum. Okay. What's that? Open circles would be appropriate here. Nice. I'm gonna take a look at the unit circle, not unit circle. Oh my, wrong class. The number line. The X going to infinity, like I was saying, we have numbers like a million. After that, we have a billion. After that, we have a trillion. They get bigger and bigger. But if X is going to 3, what kind of numbers are we dealing with? Because there's 2 right here and there's 4 right here. I think we know about that. But I hope it makes sense. If X is going to 3, there are 2 ways to do that. Right? X is either going to 3 from the left side or from the right side. So I'm going to say in this class, we're going to be talking about, Raquel, you ready for this? We're going to be talking about X going to like 3, like from the left, which means I'm talking about numbers like 2.8, 2.9, 2.99. Does that make sense that would be going to 3 from the left, right? Just like getting closer and closer and closer and closer. Could we get closer than 2.99? Could we? 2.999. Could we get even closer? Yeah, that's what I mean by approaching 3 from the left. Of course, we can also approach 3 from the right, which means we're talking about numbers like 3.999, 3.0001. Can we get closer to 3.0001? 0.00004. 3, 2, 1. That's getting closer and closer. So that's just what it means if we're approaching number from the left and from the right. That's one of the concepts we're going to be talking about today in a new type of function that we haven't discussed called a rational function. So let's get into it. Oh yeah, so some of you already noticed. Gentlemen. Homework is looking a little bit different. There are two parts of the homework. Part is in the packet. It's a couple pages, and then you'll be switching to the online portion. James?
Online, same length as it was before, or is it a little less?
Altogether, it should be about the same, but I really don't know. This is a different author. It's not me. Mr. Weiss put this together on behalf of the department. And do any of you know Mr. Weiss? Incredible man. How do you know Mr. Weiss? Oh, he did stuff for you. That's right. Yeah. Great teacher. Very, very smart. Pardon? It's a new unit and he just kind of took the lead. As a team. Yeah, we're sneaking one in. Exactly. Why? I think there was this is my first time on Algebra 2 team. I think there's just been a reshuffling. Like the first semester has gone faster than it's gone in the past, which leaves room for other stuff. So,
Did the fire is slow down?
pardon? Yes, in the past, I think it's been too slow. Like you guys did great semester 1. So like, why go slower? So we're trying to just kind of pick up the pace so that you will be also more prepared for pre-calculus.
We lost half of the fires and like the time we lost, like they cut down units or.
That did get in the way a little bit, so we would be more ahead if the fires hadn't happened.
So like we have like a few more days.
Yeah, there'll be a bunch of review days at the end. But the point is, we have time for little mini units that we're putting in here after spring break. So we're gonna be looking at,
More time for like studying your finals.
yes, there will be a review for final. Like, sure how it was in the past years. I think we have at least 2 days, probably 3, like dedicated classes to review. But I know that you mentioned that, I'm kind of interested. Let's see. Let's see what we have planned for the end of the calendar. Do you see it? The end of the year, here we are, May 30th. Here 3, just up 2, 1. So it looks like right now we have 3 days of review. And it's fine.
Do you know what day, our math exam is on? Because we do that.
I think they're gonna have it on Monday. I think they put math right after the weekend. In the past, that's what they've done. All I know is if it's probably not bad. I don't know. I don't know. One of those other classes. Yeah, Spanish maybe, Espanol. I don't know. Okay. The reciprocal of y equals x. Let's start with this. We're gonna start with a motivational example. So Kieran's aunt plans to bike 10 miles. Set distance. And I think you already know an equation involving miles from, or distance from like elementary school, don't you? Dirt. Like, would you just check with your neighbor? What's that dirt equation that Ben just mentioned? Distance equals rate times time. Are we comfortable with this? I hope we're comfortable with that. So how long will it take if she bikes an average of 8 miles per hour? How long will it take? Well, let's see. We know that the distance is 10 and the rate is 8. So the time is 10/8. What are the units here? Hours, right? 10/8 of an hour, which is a little bit strange to leave it like that. So I could write it as 5/4, or isn't that a little bit more comfortable for a question like this? 1 1/4 hours. Hour 15 minutes. 1.25 hours. How long will it take if she bikes at average rate of R miles per hour? R. But it's still 10 miles. So how long would it take her? Let's see. It's 10 equals 8 times. I'm sorry, R times T, isn't it? So T is equal to 10 over R. Okay. Kieran wants to join his aunt, but he only has 45 minutes to exercise. What will their average rate need to be for him to finish on time? Well, distance equals rate times time. The distance is still always 10. The rate, we don't know. The time, should I put a 45 there? 45 would mean 45 hours. That's a really long time to go 10 miles.
I think we know for me, if we just spend money, might be.
Look at that. We do know the time. Yeah, why were you doing redundant information? I love that. Let's go from right here. So 45 minutes, so you're saying we could put it there? You can put 3/4 here is equal to 10 over R. I'm not sure that form is easier than starting over though. I'm gonna put this 3/4 here. Either one would work. And to solve, if I solve this one, I'm just gonna multiply both sides by 4/3. Giving us with the rate of 40/3. Which is a little weird. 40/3 is the same thing as saying how many miles per hour? I think 3 times 13 is 39. So 13 and 1/3 miles per hour. And what will the average rate need to be if they only have T hours to exercise? I think we could do this a similar thing here. It's still 10 equals R times T. I'll solve for T, so T equals 10 over R. Any questions? Yeah, I'll come from D equals R times T in this case. When Kieran's, is this the same spelling as the first Kieran? Typo somewhere. One's Curran, the other's Kieran. When Kieran's ant spikes 10 miles, we found an equation that gives her time T in hours as a function of her rate R in miles per hour. It was T of R equals 10 over R. The graph is given below. So let's think about it. If her rate increases, what's going to happen to the time it takes to get her that 10 miles? It's decreasing. Does that make sense? If she goes faster, the time will decrease to go that 10 miles. If she goes slower, then the time will increase. Let's see. You see that happening here? Is this rate is getting higher? Do you see that the time is getting smaller? Wow. And she's going slower. Of course, that rate, if she's going 0.5 mile an hour, it's going to take her a pretty long time here. And if she goes 0 miles an hour, you're never going to get there. There's nothing there. Okay, so it's an acceptable domain for this function. Joseph, you with us? Please. Oh, no, I'm sorry. Acceptable domain for this function. 0 to infinity. I'm not sure if Karen can write infinite miles per hour, but I guess theoretically, if you want a spaceship that could have that capacity, go faster than the speed of light, I don't know. Write a sentence explaining the meaning of T of 8. What does that mean, T of 8?
Wait, why don't we write the speed of light for infinity? Because like we can never actually reach infinity.
It's basically infinity for us.
We're just saying hypothetical.
Infinity is faster than the speed of light. So H represents, that's the rate. So in other words, this is 8 miles per hour. So T of 8 just means the time it will take her to go the 10 miles if she's traveling at 8 miles per hour. So the time it will take his aunt to travel 10 miles is, and if I just get it from here, 8, I see it's I don't know exactly. Did we already figure out TAD? I think we did 5 hours, hour and 15 minutes. hour and a quarter. T of zero? T of zero, how long will it take if she travels or he travels 0 miles an hour? Yeah, well, I think even infinite amount of time.
It'd be zero, so they're like, it would be undefined.
It's just
Never-
a, yeah,
It could be like the y-axis.
yeah, exactly. So if someone goes 0 miles per hour, they will never arrive.
So what's the value?
Yeah. Yeah, there's really no value, is there? As R gets closer and closer to 0, what does the behavior of the function tell you about the situation? So notice again, R is getting closer and closer to 0, right, Katie? R getting closer and closer to 0. That time is going to go higher and higher. It will take longer, I'll say. It will take longer. I'll write that like a human might. Oh, there's more. As R gets larger and larger, what does the end behavior function tell you about the situation? Take shorter. Any questions? Let us continue. So a new function, 1 over x. If you plug in a 1, 1 over 1 is 1. If you plug in a 2, 1 over 2 is 1 over 2. Plug in a 3, 1 over 3. Plug in a 10, 1/10. Plug in 1,000. So etc. I think these are pretty easy math problems. And as x goes to infinity, unfortunately, 1 over infinity has no meaning. Well, what is 1 over 1,000? What is 1 over a million? Those numbers are very, very small. And as that denominator gets bigger and bigger, that y value is going to approach 0. It's about as small a number as you can get if you're not crossing over into negative territory.
So that arrow is basically like a dot on the number line, because we know it's never gonna hit 0, but it's just goes right. by.
Get close to it. Yeah, and we can see that in the graph above. And we see it like it's getting close to 0, but she's never going to be there instantaneously. But even going at the speed of light, it's going to take some time if there's distance. Okay, there's another column. If you plug in a 0, 1 over 0 is undefined. You must remember that. Anytime you have a 0 in the denominator, that is undefined. What's this? What happens when you do 1 over 0.5? What's that? That is 2. 1 over 0.25 is 4. Now notice these x values. What's happening to them? The x values. They're getting smaller and smaller. They're approaching. Does that make sense? See that happening in this column? They're approaching 0 from the right. The positives. And then these numbers, when I do 1 over 0.1, 10, 1 over 0.001. I think I could just move this over 1, 2, 3, 1, 2, 3. Leaving us with 1,000. I'm going to put in big here because I don't want to do that word. And as x approaches 0, the y values are, how big are they going to get? Is there a limit? Thank you, infinitely big. Close infinity. Yeah,
Can you explain the arrow one more time?
this one? Yeah, this is saying approaching. So on the number line, if 0 is right here, I started with 0.5. And then we did 0.25, which is right here. Then we did 0.1, you see what 0.1 would be. And then 0.001. And 0.00001. That's just saying that the numbers that we're plugging in are getting closer and closer to 0. That you can still get much closer to 0. So this is saying we're going all the way. Not actually getting there, but we're approaching 0, right, Matea? Okay. I think we're familiar with this function. I hope so. Y equals x. Okay, let's just take a look at the reciprocals of the y values. The reciprocal of 1 is 1. The reciprocal of 2 is 1/2. So I'm going to put some points here. Bring this down. No. Reciprocal of 3 is 1/3. Do you see what I'm doing here? I'm taking the y values, just take the reciprocal, or plugging this 3 into 1 over x. But 3 is, I think there's reciprocal, it's coming down to 1/3, take this 2 down to 1/2. Reciprocal of 1 is 1. Reciprocal of this 4 up here is 1/4. And you can see very quickly that I am running out of room, aren't I? I can't get much lower than that. It's going to just blend in. So this graph is going to look like, yeah, what we just did. And this y value right here, this y value of 1/2, what's the reciprocal of 1/2? So these are basically the values that we just did in the chart. 1/3, 1/4. Reciprocal graphs will always look something like this.
Horizontal and vertical, like all the same functions.
They're going to change up a little bit. They're going to have similar features. I'm not done with this. The reciprocal of 0 doesn't exist because it is undefined. But if I plug in negative numbers, like we have the reciprocal of -1 is -1. Reciprocal of -2 is -1/2, 1/3, 1/4, etc. And I can continue this. We are left with a new parent function. And you'll notice that I'm putting half arrows on this. I like to do this when it's approaching something but not touching it. That's just a convention that I use at the school. You probably won't see it elsewhere, but I really like it. I feel like it's a clean convention. If you want to put a full arrow on the ends there, that is fine. But this is a graph of y equals 1 over x. I think that already says it on here, doesn't it? Yeah, y equals 1 over x. This is the function we're dealing with here. Domain, range. Go ahead and discuss with your neighbor. What's the domain? What's the range of this function? Oh, this is one function. This whole blue is one function.
Maybe just floor ceilings.
They will get the domain? Yeah, Ben, what do you think?
Parentheses for all of this, negative infinity, comma, zero, union, zero, comma. Because you're never actually reaching zero, but you still have to include all.
Are we good with this? I hope that makes sense. I think this is the first interesting domain that we've done. Up until now, it's all been like negative infinity to positive infinity. Unless it was like one of those jagged ones where it's just like exercise wise, but this is a little bit interesting. This is a comma right here. Another way to say this is x does not equal 0.
We can just write that for domain name.
Unless it says write in interval notation. But they say the exact same thing. To be complete, you may want to also say that x is an element of the real numbers. But in my class, if I don't say otherwise, you could just say x doesn't equal 0. The range, it's not wall to wall, it is floor to ceiling. So how far down does this floor go? Negative infinity. And does it go up to positive infinity?
Yeah, but not.
It does, but there's a break, isn't there? Just like the other one. So negative infinity to 0. Union 0 to infinity, or we could say y doesn't equal 0. And y is an element of the real numbers. But if you just do this, that's fine. For my purposes in this class. Yes.
I like. Sorry, what is the Y?
Say that again. Oh.
You're saying, well, the y that I'm talking about is like all real numbers, but this is saying that it can't be 0 from that big set. Yeah, to be official, like here we're saying what it is, but what is it? So it would be appropriate to say what it is, except.
I know what's.
It just can. Wait. You know, well, one, the next class.
Okay.
Where are we gonna do the?
I'm gonna skip 2 for now. Okay, end behavior. Let's see if we could do end behavior for this new graph. Yeah, increase, decrease, yeah. As x approaches infinity, y is approaching 0, right? It's not doing this, it's not going up, it's doing this. As x goes to infinity, y is just getting smaller and smaller to 0. You can see what happening right here. By 5, it's already pretty much a 0. As x approaches negative infinity, and we can see that here. As x is getting bigger and bigger and bigger, that's what in the negative direction, these y values are getting tiny, little tiny negative numbers. Some notation that you need to know. This does not say positive 0. This says x approaching 0 from the right. From the right. I see if you think of a number line, and then 0 right in the middle, like, oh, x is going to 0 from the right. So we look at our number line, so we look at our function. Actually, I'm going to make a quick representation of it here, because I don't want to go up and down. You don't have to draw this on yours because you're able to see everything there. But as x is here, then here, then here, x is approaching 0 from the right, what's happening with y values?
Increase.
They're increasing to infinity. X is approaching 0 from the left. Those y values are going down, 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 negative infinity. So I've talked about a whole lot of stuff so far. I wanted to give you just a little bit of break from listening to me. And right now it is 23. We'll start again at 26.
So I'm not really under like this whole like little night thing. Also, like the way that this looks so weird to me because it's like a line.
Right.
So like interpreting is kind of raw.
Yes, I agree.
Well, yeah, but we also, like, that means we also think about. How often am I here? Be honest.
What?
At school?
If I wasn't gonna have any dropped.
Yeah, bro.
I would have dropped out of it.
Yeah, bro, you're.
Okay.
Only a bad.
So really what's important right now is that you understand that this function y equals 1 over x is that function that we graphed. Those two parts of the function, by the way, are called branches. And the line in the middle, do you know what that's called? That vertical line? It's called an asymptote. Have you heard of this? Have you heard of asymptotes?
Yeah, it's sad.
No?
Nope.
No, you've been going to the wrong parties then. Yeah, asymptote. There's a silent P in there. There's a silent P in there. Please don't say asymptote, like telescope,
Or isotope.
or like isotope. That's fine to have the P there, but it's an asymptote with a T at the end, please. So asymptote is I say this, a line that serves as a guide for a graph. All right, so like this vertical line in the middle is just saying, okay, you're coming to meet your guys, like saying where the line is, the graph is going.
So it's like a number where if x goes to infinity and y goes to whatever the asymptote is.
Yes, for these, yes. So polynomials don't have asymptotes. It has to be a line that it approaches. Rational functions do. So vertical asymptote. And this is the last time I'm going to spell all this out because it's way too long. I'll call it VA. Is the line x equals 0 in this case. I'm too lazy to even say horizontal asymptote. I'm just going to call it HA. The horizontal asymptote is the line, in this case, y equals 0. So horizontal line.
It looks like one of the minis and stuff like, is it gonna be on the final or there will be a test?
Okay, definitely be on the final. There'll be a mini test. Yeah, ha, of course. Ha represents horizontal asymptote. Okay, match the functions. Let's think about what this x plus 3 represents. This x plus 3 versus x minus 1. We discussed with your neighbor, what would that do to a function, that x plus 3, x minus 1? All right, this +3, would you please show me what the +3 does? It was a 3 to the left. And of course, this -1 is gonna shift whatever graph we have, 1 to the right. And we can see that quite easily when we look at the vertical asymptote.
3, 2, 1.
Now the 6, what is the 6 doing?
No, for the
What's that?
example, for the-
So,
Yeah, it's, we have the same graph just shifted here.
yes, okay.
So like which one is, well, did you already map them?
Yeah.
A goes with 3. B goes with 2. And of course, this one goes with. Are we good with that? Just by looking at the vertical asymptote, we know? Got the 3 functions using what you've learned about transformations this year. Okay, so 3 over x. Let's first graph 3 over x. What's that? Let me tell you what I want from 1 over x. How many points do you think I want here? It's a good guess. I just want 2 points. I want the point 1, comma 1. I want the points -1, comma -1. And I want 2 other features though. Vertical asymptote and horizontal asymptote. And so that's our parent function, y over x. So 3 over x is just going to take our parent function and do what with it? It's a stretch. What kind of a stretch? It is a vertical stretch by a factor of 3. In other words,
So 1, 1's gonna be like a.
1, 1 becomes 1, 3. -1 becomes -1, -3. Vertical asymptote, horizontal asymptote don't change unless there's a shift. So something like this is what we're looking for. So these are the only points that I care about. Pardon? Do calculations away? Not for this. And I don't even want it for this. We already did it for 1 over x. Yeah, so from here, all we're doing is we're taking that 1 and stretching it 3. That's why I see it. This -1 is stretched. Those are the only 2 points I care about. That's it.
So can we just like rough draw the line?
The rest can be roughly drawn. So for B, well, I have to do A, don't I? So I think we have vertical asymptote, and then that +1 is going to raise everything up. Here's my 3. Here's my 1, 2, 3. Yeah, but notice how far it is from the
Yeah.
new horizontal asymptote. That I have to move it up. So this, I moved everything up. So still 3 away from the asymptote. And now these are the guides. There we go. Last thing for C. What's that negative going to do? Flip it over the x-axis. Reflect over x-axis. Okay, I feel like I really want to stop talking. Feel like that's enough. I'm gonna give you some time for the start on the paper homework, and then when we finish that, we get to the online. Nicely done today, folks.